Let's talk for a little while about the chemical elements. Here's a periodic table that lists all 118 of them that we presently know of. We have the metals over here. We have the nonmetals over here. Along this staircase, we have what are called the semi-metals, sometimes called the metalloids. And you can see most elements exist as metals, so they behave like metals, and most of those are solids at room temperature. I might have said something earlier in the video that was incorrect. I said most of these are gases, but if I did, I was mistaken. This bromine's a liquid, iodine's a solid, astatines a solid. These are all gases up here, but carbon and phosphorus and boron. The closer to the inside of the table you get, they become solids. These are all gases right here. Those are called the noble gases. We're going to talk a lot more detail about all of that. I just want to give you some basics of what we know about the elements. Again, I want you to memorize the first 36 just to so help you name compounds easier. So that's these first 4 rows. Please memorize those symbol names and the elements. There are about 118 known elements. 90 occur naturally on Earth. 24 are produced in labs by physicists, usually in particle accelerators. Many elements you're very familiar with. Hydrogen and oxygen, nitrogen, sulfur, phosphorus. Those are all and carbon, of course. Those are all the elements that make up life. The unfamiliar ones are things like down here at the bottom of the table. Let's see, californium, thulium. They have these strange names. There's even one called einsteinium. What's the symbol of einsteinium again? I forget. Obviously it's an E. Can't find it on here right now. They named one in honor of Albert Einstein. There's uranium. You're familiar with that one because we use that for nuclear reactors. Curium, named after Madame Curie. But these are rare. They don't occur in high percentages on the Earth. Really, it's the top 4 rows that were most of the elements that are found in life forms and in minerals in the Earth's crust. Those are primarily made of these upper elements in the table. So the upper part of the table are the more common elements. And I may have mentioned this before, but there's a great website I've put on Canvas called periodicvideos.com. That is a good source of learning about these elements. The main page of the website looks like this. You click on an element and you see a nice little video from the professor in England and his research assistants, and they do all sorts of fun experiments with the elements and tell you some historical background about the elements. You'll notice that whenever you write an element symbol, if it's a single letter, it's always capitalized. If it's 2 letters, it's always the first letter is capitalized and the second one is not. There's an element called cobalt that has an element has a symbol capital C small o, this one here. But if you didn't make it lowercase for the second element, like some people write that's carbon monoxide. That's a compound. This is cobalt, the element. So you have to be careful in how you write these things. A lot of the symbol names come from Greek and Latin names. Some are from German, but most of them come from Greek and Latin names. For instance, the element lead stands for, it comes from the Latin word plumbum, Plumbum, and that's where the word plumber comes from. Plumbers work with plumbing, and plumbing pipes used to be made of lead. So that's the symbol for lead, Pb. Sodium has the symbol Na, comes from the Latin name natrium. Latin name natrium. So a lot of times it's the Latin name and the first few letters or a couple letters from the name. Helium comes from Helios, and so on. There's an interesting background in a lot of these elements, and you can learn that from going to that website. You should also watch that video, like I said, from Carl Sagan, because I think it's really, really helpful. And if you look at the makeup of the universe, like I said, most of the known universe is made up of about 91% hydrogen, about 8.75% helium, That's what's in stars, and the rest of the elements in this periodic table make up only 1/4% of the entire universe. On Earth, the most of the Earth's crust is made of rock and sand, so silicon and oxygen are very common, and hydrogen is a very low percentage, but all the hydrogen on Earth comes from, most of it comes from water and life forms on Earth. If you look what's in human bodies, most of our bodies are made of oxygen, carbon, and hydrogen. Those are the atoms that make up carbohydrates, proteins, and lipids. And there's a little nitrogen from DNA, calcium from our bones, phosphorus from DNA as well. So that gives you a little idea that there's a very different distribution of elements depending on where you're looking. So here's some of the symbols for the elements. You've seen many of these before. And a lot of times they're the first letter of the actual name, but sometimes they're not, especially if they're from Latin. Like the Latin word for iron is ferrum, so they use the first two letters of the Latin name. The first two letters of iron are IR, and that's an element called iridium. So, like I said, if you memorize them, it'll be a little bit more, it'll make your life a little easier in this class. What else could we talk about? I can show you some elements. For instance, I work on pianos, and copper is used in piano strings. We all know what copper looks like. Copper piano strings have hundreds, if not thousands, of copper windings on them to make a piano string. And the longer the string, the lower its pitch, and the more copper it uses. It's the same element that's in a shiny new penny, but we don't make pennies out of copper anymore, of pure copper. They're only copper-plated zinc. I think you have to go to pre-1982 pennies to get 100% copper. And I actually will need you to try to find some so we can use them in the Cycle of Copper lab. So if you do remember this little message I'm giving you, please bring some pre-1982 pennies to lab. I would appreciate it, because we need pure copper to do the Cycle of Copper lab. Aluminum foil is pure aluminum. That's right here. It's on the metallic side of the periodic table. It's actually very close to being like a non-metal. So, but it's obviously a metal. You can pound it into sheets. You can conducts electricity. Now, if you wanted to get to if you looked under a microscope at this to see the actual atom, you'd actually have to tear the foil into about 90 pieces if you could actually do that. And then if you tore this 90 times, you'd actually get down to seeing aluminum atoms. Helium is very common. This carbon is an interesting element because there are three common forms of carbon. There's diamonds that have carbon atoms locked in a rigid structure. Those black spheres represent carbon. This is why diamonds are so, it's the hardest substance known, because it has a very rigid, stable chemical structure. Carbon is very happy in this arrangement, so it chemically does not react with anything. And it has a very high melting point and very high boiling point. The other common form of carbon is carbon atoms when they're only bonded to three other carbons. And therefore, when they're in this arrangement versus this one, they have these have the ability to conduct electricity. So graphite actually can be used to conduct an electric current. And graphite is a black powder. Carbon is all black, just like a few charcoal briquettes that you use on your grill. Graphite looks like a black solid, but it's kind of shiny and it's slippery. You can use graphite like this as a lubricant because it's very slippery. It's the same. This is the same stuff that's in pencil lead. We say pencil lead, but it's not lead. It's graphite that they use. And the reason why it's slippery is because what's happening is these sheets of carbon are sliding past each other. They actually are made, graphite is made, these particles you see on my hand and on this paper are made of these big sheets of carbon atoms, and they can actually slide past each other. And that's what gives it that slippery feel. About 36 years ago, in 1984, I believe, they discovered a third form of carbon that, believe it or not, actually looks like a soccer ball. They call it buckyball. It has nothing to do with Bucky Badger. It's named after a famous architect named Buckminster Fullerene. he evidently made these houses that were shaped like geodesic domes. As if you imagine cutting this in half, you'd have a geodesic dome, and he made houses like that, or he designed houses like that. So they named it in his honor. But it actually has carbon atoms that are shaped in the five-membered rings, like a soccer ball, and then next to it is a hexagon, which is the exact same geometric structure to a soccer ball. So that's just pure coincidence. But there's a lot of research today on buckyball and inserting metals inside of them. Maybe they have a future use in medicines and vaccines and things like that. What are some other interesting elements? Iron is very important to us. Iron's name comes from the Anglo-Saxon word for iron. So we didn't change it. I'm just reading from some pages I printed off the internet. But iron is critical for us because in our red blood cells, this is a hemoglobin protein. It's made up of 4 protein chains, color-coded here. And inside the center of each subunit of hemoglobin is a molecule called heme. And at the center of the heme molecule is an iron atom. So if you're anemic, you have low iron in your blood. So you have a hard time carrying oxygen throughout your blood. But when you breathe in and out, you're actually carrying oxygen on these little parts here. We'll talk a little bit about that when we talk about covalent bonding a little bit later in the class. I've already showed you a real sample of copper piano strings. Copper was used to make the Statue of Liberty. The Statue of Liberty has turned green after many decades sitting out in New York Harbor because of acid rain. It's oxidized. That coating on it is copper carbonate and copper acetate. Ionic compounds formed when acid rain falls on the statue, and then chemical reactions occur to oxidize the copper. When copper dissolves in water, it makes a bluish or greenish solution, and that's what you see there. That actually makes a protective coating on the statue and helps it last longer. Copper is also used to make musical instruments and brass hinges. If you mix copper and zinc, which you will do in lab in what's called the gold penny lab, you're going to make real brass like that. That's an alloy. That would be classified as a solution, a solid solution. Silver is a very interesting element. This is what happens to you when you ingest too much silver. You turn blue. This guy has a condition called argyria, and I'm not sure if he's still living. He lived a long life after this, but his skin turned blue because he ingested too much colloidal silver, which was silver suspended in water. It was supposed to have some sort of health benefits. I'm not sure if that's true or not, but silver is one of the greatest conductors of electricity, even better than copper. And the reason why metals are good at conducting electric currents is because their electrons can flow very easily throughout the metal. So they're used in electric circuits. Copper is used because it's somewhat affordable versus silver. I forgot to mention earlier that I'd like you to also memorize the 7 diatomic elements. They are H2, N2, O2, F2, Cl2, Br2, and I2. They look like this, and when we draw, these are called Lewis structures, and when we talk about that in a little few weeks, you will understand where those structures are coming from. But they occur naturally in nature like this. They don't occur as single elements. They always occur with another atom of themselves to make a stable molecule. And it's easy to remember them because if you look, hydrogen's here, nitrogen's here, oxygen's here, fluorine's here, chlorine, bromine. They kind of make a shape of a 7 if you draw the connectivity out. So that's easy to remember that there are 7 of them. All the other elements in the table, or most of them, occur as single atoms if you looked at them under a microscope, or if you're actually able to see the molecules themselves. The next topic I want to review with you is what's called physical properties and chemical properties. So we need to distinguish between those two, physical properties and chemical properties. So again, chapter 1 is just a way, it's summarizing all the terms we need to learn to move on in the course, and also just how do we organize matter, how do we classify matter. There's physical properties, there's chemical properties. Chemical properties are, I'll give you some examples, but they are what we're going to be more interested in this class. Physical properties are a little easier to understand, but let's give you some examples. What are some examples of physical properties? Physical properties are properties of an element or a compound that don't cause a change in the chemical formula. The substance makeup doesn't change, but you can change the physical state, or you can observe a physical property by not changing the chemical makeup, density, color, melting point, I'll abbreviate MP, boiling point. Those are all physical properties of a substance. And we'll go through some more examples in a little bit. Examples of chemical properties. Try to think of some. Anything that causes a change in the formula of a compound, causes it to convert into something else, is a chemical property. So it's chemical reactivity. Its ability to burn, its combustibility, its flammability, but it changes the substance. So chemical properties change the formula of a substance. So for instance, observing a chemical property of, let's say, sodium would be taking sodium, mixing it with chlorine to make sodium chloride. That would be an observation of a chemical change, because over here it's sodium chloride. Sodium is part of sodium chloride. Over here it's elemental sodium. They're completely different compounds and with different properties. Some other examples. These are some properties of water, sugar, and baking soda. The physical properties are of water, it's colorless, sugar, it's white, baking soda, it's a white powder. They're all odorless. Melting points are, you can observe the melting point or boiling point without changing the chemical composition of a compound. Chemical properties of these compounds would be their chemical makeup, their composition, what percentage of each element is present. Do they burn or do they not burn? That's flammability. That's a chemical property. And we also have what are called physical and chemical changes. So what's a physical change? A physical change does not alter the chemical makeup. Does not alter the chemical makeup of a substance. I'll try to minimize how much writing I do. I'll just give you slides that you can actually make your own notes from. Its chemical reactivity is unchanged. Changes in state, changes in particle size, the formation and separation of mixtures. These are all examples of physical changes. Melting of ice, boiling point, boiling of water, and things like that. Let's give you some other examples that will help clarify that. If you, for instance, if I take this piece of aluminum foil, how do I observe a physical property, or physical properties of this would be it's shiny. I can pound it into sheets. I can crumple it up into a ball. I don't want to do that right now. I can tear it. That's a physical property. But that's what I just did there, was a physical change. I can tear it. Like I said, if I took the piece of aluminum and ripped it in half, and then I took this piece and ripped it in half, and then take this piece and rip it in half. Well, if I ripped it in half, was careful, and then kept going, it would take about 90 times before I'd get down to an atom. But my fingers are too big. I can't rip it that many times. But these are physical changes. This is still aluminum, as these larger pieces are still aluminum. I'm not changing the chemical makeup of the aluminum. I'm going to insert a really cool video at some point in this video where I show you that the chemical change of aluminum that you can undergo is if you react it with bromine. You can just take this little piece of aluminum, kind of fold it up like this, and then put it in a test tube and add elemental bromine. Elemental bromine is this substance here. It's one of the 7 diatomic elements. It's Br2. These elements in this column are super chemically reactive. Fluorine is the most electronegative, probably the most chemically reactive element we know of, one of them at least. Bromine is right near it in the table, so these are all very chemically reactive. You can take a piece of aluminum foil, put it in bromine, and you will see something spectacular. It will form almost a fireball of a new compound. The fire that it releases is just the heat that's released when a new compound called aluminum bromide is formed. And I'll insert that at some point here in the video. Let's see what else. Evaporation of water from a lake is a physical change. Chopping wood is an example of a physical change. It's still wood. You're not cutting the wood. I mean, you can take a piece of wood and just cut it up. It's still wood. You're not converting it into anything. A chemical change with wood would be burning it in a campfire. You're converting the carbon and hydrogen and oxygen of the wood into CO2 and water. Crushing a soda can is a physical change. Dissolving salt. When you make a mixture, dissolving salt in water, as I showed earlier in the videos, that's a physical change because I can just get the salt and back. If I just evaporate off the water, I can get the sodium chloride back. Dissolving sugar in water is a physical change. Even melting butter is a physical change because I can cool the melted butter down and I get solid butter back. So I haven't changed the chemical makeup of the substance. Now, chemical changes are a little bit maybe harder to see sometimes or predict. But again, the video I'll show you probably right now can be written like this. You take aluminum and bromine and you make a new compound called aluminum bromide, which is a solid. That isn't balanced yet, but we will talk about balancing equations at a later time. But chemical changes alter the chemical makeup. So it alters the makeup of the substance. What's the makeup of a substance? It's its formula. Its formula is going to change. Heat and light and electrical energy are often emitted when you observe a chemical change. For instance, if you go to that periodic videos website, and you'll see a really cool video under potassium. They react potassium with water, liquid water, and you form potassium hydroxide, which is aqueous, and hydrogen gas, plus a lot of heat. It explodes because potassium is so chemically reactive. It's a very violent reaction. Some other examples of chemical changes would be burning magnesium. I'll show you that in laboratory. That's a cool reaction. That's what you see when you see those white fireworks falling in the sky. That's magnesium burning. Put a 9-volt battery in water. You can observe the electrolysis of water. You can ruin the battery too, but you'll actually see bubbles coming off the battery. That's hydrogen gas and oxygen gas coming off of the battery. The battery is providing enough electricity to the water to break the water into its components. H2O becomes hydrogen and oxygen. That's a chemical change. Milk going sour is a chemical change because sour milk makes you sick, tastes terrible, and so therefore it's made up of different chemical compounds. When jewelry oxidizes or tarnishes, that is a chemical change. A penny turning dark brown. I have a bunch of pennies here. This is an observation of these have undergone chemical changes. Here's a new penny. I scrubbed it with some steel wool. You give it a couple years, it darkens a little bit. Give it a few more years, it darkens even more. Give it a long time, it turns almost black. That's a chemical change. Over many years, oxygen in the air has formed a coating of copper oxide on the penny. So now you have CuO on the surface of the penny and not just copper atoms. So a new compound is formed, and this is a chemical change. When you burn gasoline, burning fossil fuels, gasoline burning a campfire, burning wood, those are all chemical changes. Frying an egg. I think you get the point. Fireworks exploding. There are actually many examples. There's probably more examples of chemical changes than there are of physical changes.
To start, bromine is added to a test tube. This is bromine that was made in a previous video and it was stored in my homemade ampules. I show here that it can be easily opened by breaking it open with a pair of pliers. Then, aluminum foil is added to the test tube. Due to the protective oxide layer on the outside of the aluminum, it takes a little while to react. The aluminum reacts violently with the bromine to form aluminum bromide.
I hope you enjoyed that little video I spliced in showing aluminum foil reacting with bromine. It's a very violent reaction, as you can see. A lot of reactions are like that. They give off a lot of heat and light. They're called exothermic. Another exothermic reaction that we use is the burning of fossil fuels, like the one I have here. But I just want to clarify for you the way we describe matter and its properties can be described with 4 terms. We've already discussed physical and chemical properties or changes, and there's a couple more useful terms: extensive versus intensive properties. So if we look at this reaction, we're observing physical properties if we just observe that methane's a gas, oxygen's a gas, CO2 is a gas, and water's a liquid. We're not, by observing those things and making those observations, we're not changing the substance. We're still, its chemical makeup is unchanged. They're all colorless gases. The fact that they're colored or water's a colorless liquid, we can observe that by not change or alter the chemical makeup, the formula. So those are physical properties and changes. Observing a chemical change, as I said before, is observing something that will cause it to change into something else. So CH4 burning in oxygen, becoming CO2 in water. The carbon is changing its form and bonding to different atoms. That's a chemical change. Observing or calculating the composition of water to be 11% hydrogen and 89% oxygen. That is a chemical change or chemical property. Extensive properties observed in such a reaction would be the volume of oxygen needed to burn this methane, or the mass of CO2 produced. We need to worry about things like that when we talk about air pollution. We're trying to minimize our use of fossil fuels and minimize how much CO2 is being put out into the atmosphere. But the amount of CO2 that is produced or the amount of oxygen needed, those are extensive properties because they depend on how much matter you have. The more matter, the more CH4 you have, the more oxygen you're going to need, and the more CO2 you're going to form. That's extensive. Intensive properties are inherent qualities of something. So observing the fact that the density of water is 1 gram per milliliter is an intensive property. It doesn't matter on how much water you have. A swimming pool of water has the same density as a coffee cup filled with water. It's 1. Observing the boiling point of a cup of water to be 100 degrees C versus the boiling point of a lake or a swimming pool. They're both going to have a boiling point of 100 degrees C. That's intensive. That's the difference between the two. Now, all these things we're talking about in this class, all these observations, all these theories are part of what's called the scientific method. I'm not going to spend too much time on this. I just want to briefly summarize it. Understand that everything that I'm telling you and that we've learned, and then future scientists like some of you will help develop new theories and new scientific laws, but you are all going to follow the scientific method. It's just a philosophy of how we conduct science and how we conduct experiments. So over the centuries, people have made observations or performed experiments, and they observe patterns. See if you can think. What might they have observed over the years? Let's see. The fact that the sun rises in the east and sets in the west. And it takes 24 hours. Those are observations, and they came up with a theory. The theory that the Earth revolves around the sun. And so that's an explanation of how things occur. It's a very simple example, but that's following the scientific method. Um, but if you observe patterns and you come up with a hypothesis is an if-then statement. If something is true, then this will happen. So hypothesis will predict future results, and you can observe those future results by doing more experiments. So the scientific method is a cycle. If you find that the results of your experiments are repeatable, or the hypothesis predicts future results reliably, then it becomes what's called a theory. A theory is an explanation of how something occurs. So the theory of relativity is very famous. It explains why time slows down when you travel close to the speed of light. We call that time dilation. Or the theory of evolution, how we've come about from millions of years of evolution. Now there's things called laws, scientific laws. The ideal gas law we'll talk a lot about in this class. It's a simple mathematical statement, PV equals nRT. Scientific laws are not theories, they're explanations of what happens. We've made lots of observations and we usually summarize it in a simple statement, usually an equation. Force equals mass times acceleration. I believe that's called Newton's second law. Isaac Newton was a famous physicist who invented calculus, and he had some famous laws. These are understood to be they're always true. The law of conservation of energy, the whole universe obeys that. There's only so much energy in the universe, we just convert it from one form to another. So that's the difference between a theory and a law. A theory explains how something happens, and a law explains what happens. And I found a couple videos on YouTube that I'll splice on to the end of this one. One is from a famous astrophysicist named Neil deGrasse Tyson. You've probably seen him on TV. He gives an everyday example of how the scientific method can be used or how you've used it in your everyday life. And then I'll put a little short video that explains the differences between theories and laws.
There was an incident in Pasadena, California. I was there. I don't drink much coffee. I don't have a relationship with caffeine, but every now and then I'll be delighted to have a nice cup of hot cocoa. And I went to one of these coffee houses, with the chalkboard out front. And so I had, the kind I'm talking about. They're all over Brooklyn. You trip on the chalkboards in Brooklyn. So I'm in there, I order hot chocolate, and I order it with whipped cream, of course, right? And it comes to the table, and there's no whipped cream. And I said, I ordered this with whipped cream, and they said, oh, we put it on. And I said, well, where is it? Oh, he said, it's sunk to the bottom. I then said, either the laws of physics that apply everywhere in the universe are suspended in your coffee shop, or you didn't put whipped cream on my hot cocoa. And he looked indignant. Really? Now, to his credit, rather than continue to argue with me, he intended to prove me wrong. So he went into the kitchen, brought out the whipped cream, scooped it up, popped it in my hot cocoa, and it bobbed once and floated atop. And there it was. Did you of course whipped cream whipped cream has to float. Because, first of all, before it was whipped cream, it was cream, okay? And old-timers remember, what does cream do in unhomogenized milk? It floats to the top, and you skim off the cream, leaving behind skim milk, okay? This is how that works. Now, you take the heavy cream and then whip it, putting air into it. It is not going to sink on any known liquid devised by man, okay? So, all right. So here's my point. The lesson there is, yes, I'm a fan of the edict. If an argument lasts more than 5 minutes, then both sides are wrong. I think that applies maybe 85% of the time, but it's a good rule, it's a good tenet to carry with you. Now watch. This is how science works. One researcher comes up with a result, and that is not the truth. No. A scientific emergent truth is not the result of any one experiment. What has to happen is somebody else has to verify it. Preferably a competitor. Preferably someone who doesn't want you to be correct. Such as my waiter. He went out to prove me wrong and got the same result that I had declared. We can call that the beginnings of an emergent truth about whipped cream. Now we need someone to do it in Asia and in Europe, and then you get a trend, and you can then declare that a consensus of observation and experiments has emerged in the scientific community. Whipped cream floats on hot chocolate.
And that waiter today is getting a PhD in points.
Scientific theory versus scientific law. It is important to understand the similarities and differences between a scientific theory and a scientific law. Both scientific theories and scientific laws describe something that has been observed in nature. They both require many observations and experiments, and they both must be accepted by the majority of the scientific community. However, scientific theories are not laws, and they are not treated the same as laws. Unlike a theory, where evidence changes, a law will never change. In science, a theory is a widely accepted explanation supported by abundant scientific evidence. Theories are not just ideas or guesses about how something works, and theories are not just opinions about a concept. For science to prove a theory, scientists must conduct extensive tests and experiments. A theory must be supported by tremendous amounts of scientific evidence, and it must go through peer review and retesting. Even if a theory is proven, it is subject to change in the light of new evidence. This is the best way for science to evolve and change. In this way, scientists can use theories to build upon the evidence and ideas of other great minds. One good example of a theory that has evolved over time is Newtonian mechanics, first theorized by Isaac Newton in the 1600s. This theory explained the movement of objects, both on Earth and in space. Using Isaac Newton's work, Albert Einstein perfected the theory, renaming it the theory of special relativity. Einstein's new theory put a twist on the Newtonian theory, allowing us to measure objects in reference to space and time. Einstein even upgraded his special relativity theory to a more current version that we use today, the theory of general relativity. Scientific laws are different from scientific theories. A scientific law is a description of a fact that is completely accepted in the scientific community. A scientific law does not change, and if it is refuted, not only does the law become false, but all science that was based on that law also becomes false. Laws state that something in the natural world happens, but they do not necessarily explain how or why. The law of gravity, for instance, states that all objects have a force of attraction for each other. This law explains what happens, but not how it works or why. Theories attempt to explain the how and why. When trying to decide if something is a scientific law or scientific theory, ask yourself this question: does it explain what happens, or does it explain how and why something happens? If it explains what happens, you are talking about a law. If it explains how or why something happens, you are talking about a theory.